Can you hear me? Perfect. So good afternoon. A number of people managed to survive till the last session. So I'll be talking about generating student feedback for introductory programming assignment, and by using program repair and leveraging a large number of existing correct solutions. So this morning I've asked how many of you is doing grading, and quite a number of people raised hands. So how many of you think this is a very fun activity? Yeah, that's what I thought. So I think one could better describe it as something that's quite time-consuming, tedious, and in the end quite error-prone. And when we add to that there is a rising demand for programming education, then I think that it's quite justified that we don't do it manually, but that we automate this task of grading and, or more general, providing any kind of feedback for programming assignments. And what I'm going to talk about is using PL and formal methods techniques to do that. So as a warm-up, here is a problem that I will use as a running example through this talk. So the students are given a task of computing a derivative of a polynomial function that is represented as a list of floating point coefficients, and the corner case is when derivative is 0, the returned list should not be empty, but a list of 0, 0. And on the left, we can see one correct implementation for this task, and on the right, we can see one incorrect implementation of this task. And so the goal is to help the student who wrote code on the right to come up towards the correct solution. So at many universities today, and any programs where students learn how to program, this is usually done by presenting students with failing test cases, like given here. So when the program is not correct, students are given some inputs, expected output on it, and the result of the student program. Now this is very good, since it mimics how actually developers debug their programs. But there is a problem with that. Somebody who is learning how to program, this might be quite not helpful. I mean, for them, they need more guidance on how to continue. So what would be more guidance? So for start, one could tell the student where the error is, so they know where to look even for errors. So just showing them the locations where the errors are. But even more guidance could be to tell them what's wrong. So for example, in the first expression, that they should start iteration from 1 instead of 0, that they should use a Penton list, that assigning to list in Python is not meaningful, and that they're missing the corner case of returning the 0, 0 list. And next I'm going to talk how we do that by using program repair and, as I said, leveraging existing correct solutions. So here is the overview of the approach. So the input to the feedback generating procedure is a number of correct student solutions, here marked from A to F, and an incorrect student attempt marked G. The first step in our approach is to cluster the correct student solutions into classes based on kind of dynamic equivalence, semantic equivalence of traces. Now, it might be not clear why we are doing this clustering, but bear with me a bit and it will become clear why we need this clustering. Then the next step is to use these clusters to repair student incorrect attempt, and this is by taking each cluster separately and running repair algorithm on a cluster and incorrect student attempt, which gives us repairs for each cluster, among which we pick the smallest one and generate the repair from this minimal, generate feedback from this minimal repair. So first I'm going to explain how the clustering works, then repair, and conclude with experimental evaluation of our approach. So to explain clustering, as I mentioned, clustering is done on correct solutions. So here are two different correct solutions. These two solutions, they differ in variable names and other syntactic differences, but we want to put them in the same cluster because they are semantically equivalent on the traces they produce. How do we conclude that? We execute both programs on the same input. Here we have this input, and let's for now observe the values that variables result and derive take on this input. So when we start executing them, so in the beginning, before the loop, both variables take empty list. Then in the first, this is the result of the first iteration of the loop. Then in the second iteration of the loop. And then finally, this is the value of these variables after the loop. They take the same values, so we say that the expressions assigned to these variables, they produce the same values over the whole execution. And not only these two variables, we have this this property holds also for other variables from this program. So for example, I takes the same values as E, and return values are also the same. We say that these two programs match, witnessed by this relation between variables. And this is our condition that these two programs belong to the same cluster. Now, these are two expressions that these two programs were assigned inside a loop. The second expression was obtained from the second program by using this variable relation to rewrite variables to range over the same variables that the first program ranges. And in the test data that we have for evaluation, we have seen many different ways to write this same expression inside the loop. So there are many syntactically different, although semantically equivalent ways to write the same thing. So this is the same expressions also for the return expression after the loop. Also, one can write it in syntactically many different ways, although they're semantically equivalent. And so the key idea of our approach is to collect these correct expressions and use them to repair incorrect programs. So next I'm going to explain how this repair procedure works. I want to mention that the repair procedure that I'm going to describe is against one cluster and one incorrect attempt, because the repair procedure in parallel can run repair procedure against multiple clusters and picking the smallest one. So the idea of repair is to generalize the clustering from correct programs to the incorrect programs. The idea is to minimally modify incorrect program such that it matches the programs from the cluster, meaning that it belongs to that cluster. So how can we do that? Well, we pick some variable relation between these two programs. As we said, this is a witness that two programs match. Then, for each correct expression in the program, we leave it unmodified. And for each incorrect expression, we replace it by the most similar among the collected expression in this cluster. Now it's important to note here that we cannot just pick variable relation. We have to find the one which defines the smallest repair. And in this talk, I'm going to abstract over that. The algorithm for doing that is a bit more too technical for this talk, but the details are in the paper. So here, we are going to assume that this variable relation is magically given to us. So let's see an example. On left, we have correct program, the same one which we have seen before, which we have used in clustering. The input to repair procedure is also denoted down a database of our collected expressions. And on the right, we have one incorrect implementation of this program. And the algorithm, as I mentioned, as a first step, we come up with the variable relation between two programs, between the incorrect program and a correct one. And now we examine the correct and incorrect expressions in this program. So we start, result and new are definitely taking the same values. So new is a correct expression because it takes the same values as the one in the reference cluster result. Also the loop iteration also takes the same value, although note here that they are syntactically different, but they do take the same values and hence they are correct. Also the expression inside the loop is correct because it takes the same values as the reference expression. But this expression is not correct because it returns the wrong value for the empty list. And now we take the database of collected expressions. We find the expression which is the most similar to the expression that we have in the incorrect program. We take the variable relation which was provided in the beginning and rewrite this expression to range over variables of incorrect programs. And we replace it in the incorrect program, and the program is now correct. And this change can then be reported to the student as the feedback, as what they should do to make their attempt correct. Okay, let's do one more example. This is the one which we have seen in the beginning. This is a bit more complicated. Again, we are provided some variable relation. And then we start again with the same thing. So the first expression is obviously correct. Then this expression is no longer correct because the iteration starts from 0 instead from 1. This expression will also throw exceptions, as we have seen in the failing test cases example. And finally, the return expression is also wrong. And so we again pick from our database the most similar expressions for these wrong expressions. We use the variable relation to rewrite them to match, to range over the variables of the incorrect program. We replace it in the incorrect program, and then the program is correct. So I would also like to point out that this approach, it can perform even more complicated repairs than shown here. So we can introduce new variables that do not exist in the incorrect program, can insert or remove statements, and change the order of statements. And finally, I would like to discuss our experimental evaluation. So our first experience was on MOOC size. And I've been pointed by some people that maybe somebody doesn't know what a MOOC is, so that's a massive open online course, although I'm convinced that most of the people know what that is. And so to evaluate our approach, we implemented it in a tool called Clara for cluster and repair, which is also publicly available. And we took a data set of nearly 13,000 correct solutions, and we clustered them and used them to repair around 4,000 of incorrect attempts. And these programs are written in Python, as had been these examples. And Clara is able to generate repairs in 97% of the tools, which is not surprising. If you think about the algorithm that I've presented, you can imagine that there is always a trivial repair where you just rewrite the incorrect program with the correct one. And it's quite fast for generating feedback for students, so it's around 3 seconds. But since we can almost always generate the repair, the more important question is, are these trivial repairs that we are generating, and what's the quality of these repairs? So the first experiment that we did was see what is the relative size of the repair. So if we divide the size of the repair by the size of the program, how does it look like? And you can see here the histogram of that. Most of the repairs are on the left side, so they're rather small, except there is this spike on the right because dataset contains some completely empty programs, so their relative size is actually infinite because their size is 0. And additionally, we also manually inspected around 100 random repairs. And how did we inspect them? So we would take a look at the incorrect program and think what would be our feedback to the student. And in 81% of the cases, we came to the conclusion that the tool generated the repair that also a TA or a reasonable teacher would also provide to the student. So that was the first experiment that we did. Next experiment was user study by generating feedback in real time to the users. So we had 52 participants in our user study. We gave them 6 programming assignments, and while they were solving them, whenever they submitted an incorrect attempt, they would get a feedback generated by Clara. And these 52 participants on 6 programming assignments, they submitted around 1,500 incorrect attempts. And Clara was able to generate feedback for 88 attempts of them. And when participants finish the solving some exercise, they were presented with the question of whether the feedback that they were presented was useful. So they could grade it from 1 to 5, where 1 was not useful at all, and 5 was very useful. And the participants graded it with median grade of 4. And as you can see on this distribution, more than half of it, around 60%, were 5 and 4, which we believe is quite promising initial results. And here you can also see some comments that participants left. Some of them are positive, but there are also some constructive but not so positive comments about what should be done, and that gives me the opportunity to talk what should be the future work in this area. So I would divide it in 2 parts. One would be technical, like coming up with more sophisticated repair or whatever algorithms. So for example, on our approach, what could be done, where we could do more research is see different cost functions. So right now we are comparing the syntactical differences for repairs, which is not always ideal. Then our approach is limited almost to the same control flow, so it would be useful to see if this can be lifted. But also, what's very important and could be seen on these comments, the other part is pedagogical side. So for sure, it's not useful to show students the whole repair, because then they don't learn anything. So there is more research needed on what kind of feedback we want to provide from repair, how much students learn from that, and so on. So to conclude, I have talked about fully automated repair algorithm that uses expressions mined from multiple correct solutions that already exist. And our experiments show that these repairs are small and of good quality, and our user study shows quite promising results. And I want to mention again that we have a publicly available tool, Clara, which also some people started using for research in pedagogy, so how to use repair. And I'm also going to shamelessly use this time to also advertise some open positions. So if you're interested in program synthesis, there are open intern and full-time positions at Microsoft's Pros group. And also in Austria, there are open PhD positions in logical methods and computer science in Vienna, Graz, and Linz. Thank you. Please, questions.
So we do have time for questions, and please do queue up at the microphone. And Ivan is ready.
Thanks for the talk. Could your technique be used to detect plagiarism between students in a class?
I think that could probably be possible, because perhaps the clustering part of the algorithm might be useful for that. But I don't have much experience in plagiarism detection, so I have no actual clue. But it seems to me that it could be useful, the clustering idea.
Cool. Great talk. My question is about the feedback. I was sort of browsing through the paper, and I don't think you mentioned particularly what sorts of feedback you were giving the students in the study. So I was wondering if you could expand on that a little bit more.
So it was mostly the repair.
Was it the form of, this is the suggested repair you should make?
Yes,
specifically?
yeah, but if it was too large repair, then we would only show part of it and not show all the modifications, but the topmost 3 or something like that. But it was still a repair, so we didn't do anything more fancy there.
All right, cool, thanks.
Thank you.
It feels weird to have to ask this question, but how well do you think this would work on a smaller class size?
Well, our user study was quite a small class, so user study was, I see the confusion.
But you had 1,500 wrong, or no, 1,500 prior attempts to work
no,
from,
that was
right?
1,500 incorrect attempts.
Okay.
So
How many
yeah,
correct
I didn't go
attempts
into
were you
details
using?
here, but you can find that in the paper. So this user study was done on programs in C, not on MOOC data. And we basically took it from a course in India, where they have like 50 students or 30 students, I think, per solving one exercise. So we didn't have a huge data available. But what we did during the user study was collect correct attempts during the study.
Right, so a corpus of like dozens instead of thousands turns out to be enough?
Yes, but we have also noticed that then the quality of repair goes down.
Yeah, sure.
Because you have less available repairs.
This looks really good, and I just marked 200 JavaScripts, and I'm wishing I had access to this. But I actually spent a lot of my time commenting on style and commenting on some OO principles and that kind of thing. So there were students who passed all the tests, but still didn't get a very high grade. Apologies if you said this at the beginning, but is the notion of something being wrong and needing to be repaired based on failing tests, or is it also based on other criteria like poor style? Can you encode other notions of needing to be repaired?
So this particular work is considering only functional correctness, so that means passing or failing test cases. We have an earlier work which is considering also performance aspects of student attempts. So this is also an interesting thing, and one could also, in the same way, try to analyze the variable names that are used inside or various stylistic or formatting criteria. But this work is considering only functional correctness.
But could you just call out to some black box that says whether the thing is good or not, and then use your approach?
So I would say for...
Like if I would write a style checker, could I use the style checker as the notion of whether something is correct or not, rather than tests?
Yeah, I mean,
then,
as long as we could partition the solutions into correct and incorrect, yeah, I don't see why it wouldn't work.
And it's language independent, is that right? You did it for C and Python. Could I use it for Java?
Yeah,
I'll look at the web.
I mean, it would actually you could. I mean, the tool can be extended. You just need to write some part of it, but the core algorithm is independent of the language.
Cool. Thanks for the talk. Do you have experience using the output of this for grading as opposed to giving feedback to the students on how to improve their solution?
Well, I think you could use it for grading. Probably would need to analyze what was the output if the repair was big. I guess you would give like the lower grade. If it was only a small mistake, you would probably give a better grade. I mean, that would be my take on it. But this is just without too much thinking. But I guess you could use it in that way.
Okay, thanks.
One quick question for me, and then we'll switch to our other speaker. You do the clustering ahead of time, which obviously makes sense. But that means you're going to use the same clustering both for large repairs and small repairs. Do you have any sense of whether maybe a couple, 2 or 3 different clusterings would be more helpful in order to sort of better optimize for different size of repairs?
That I did not think about. Possible. I think it might be possible.
Let's thank you, Ivan.